Hi everyone. Today I'm going to talk about two main aspects to consider in Wi-Fi: range and data rates, and you will learn how they are related. I will use some pictures and some resources shared by the Wi-Fi community. When electromagnetic waves propagate through the air, they experience several types of alterations as they encounter different types of obstacles, and it also decreases by the propagation itself. It is called free space path loss. A physical law states signal power dissipation is inverse to the square of the distance, as you can see on this image. There are several formulas that will demonstrate this. An even simple way to estimate free space path loss is called the 6 dB rule. The 6 dB rule states that doubling the distance will result in a loss of amplitude of 6 dB. You can see on this image. We are going to do the math in order to demonstrate this. Okay, we have free space path loss. The formula is here, and we are going to substitute some values. For example, we have the distance in miles. We are going to evaluate the first meter. So 1 meter is equal to 0.00062 miles. Besides, we need to substitute the frequency that we are going to use. So in this case, we are going to evaluate 2.4 gigahertz. If we substitute all these values, we will obtain approximately 40.05 dB of loss. Okay, you can see this value in 2.4 gigahertz, and the green value is for 5 gigahertz. Now, if we use the other formula that is related with the inverse square law, we can see the following. A loss of 40 dBs is equal to milliwatts. Okay, we can see this as an intensity, and if we use the formula for the inverse square law, it says that the intensity is the inverse of the square of that distance. If we are evaluating 1 meter, let's say that it increased the double of the distance for 2 meters. So intensity should be divided by 2 meters at the square. I will say intensity divided by 4, which is equal to 0.0000025 milliwatts. If we use a converter in order to see what this value corresponds to dBs, it should be a loss of 46 dBs. Okay, so we have the relationship between the two formulas. Later on, if we use this table to take the value of the loss of 40 dBs, we can see the values that we used on the formulas before. Now I'm going to use this table because sometimes we are going to use milliwatts or dBms indistinctly. So it is better for us as a wireless engineers to know how to do in a faster way. We are going to use this table to show something called trees and tens rule for this conversion. So you can see here at the top, we start with 20 watts of power, which is equal to 43 dBms. And the trees and tens rules states that if we decrease 3 dB, which is here, by another hand, we have half of the power. So half of the power of 20 watts is 10. So we are demonstrating that relationship. If we do the same for the second, the next row, we can see here, for example, we are going to demonstrate another rule for the tens and trees, which is, for example, if I have 40 dBs and I have a decrease of 10 dBs here, in the other side, we will have a decrease of 1/10 of power. Okay, so you will see that 10 watts divided by 10 is 1 watt. Okay, the relationship between dBm and milliwatts is logarithmic, as you can see on this image. And you can see the formula here, and you can see the equivalents that we use on the table before. So we are going to use this, for example, in order to reinforce the trees and the tens rule from here. I'm going to draw a table with values. So in this case, we have on these sides 20 dBm, and on this side we have 100 milliwatts. If we use the formulas or the rule that we used before, we will have, if we have an increase of T 10 dBs, we will have multiply the 1 milliwatt for 10. So if we have another increase of 10 dB, we are going to have to multiply 10 milliwatts by another 10. So we are demonstrate this rule. The faster way to use this table is use this as a following template. We have 0, 1, we have here the dBm, we have the milliwatts. So if we have an increase or lost, we have here a multiply or dividing. If we here have 10, on the other side we will have 10. If we have 3, on the other hand we will have 2. So this is basically the template that we will use for making these calculations. Propagation behaviors that cause attenuation include some effects like reflection, refraction, diffraction, scattering, and absorption. Reflection is when the electromagnetic waves run into large obstacles such as the ground, walls, or buildings. They reflect and change their direction and phase. Scattering, when electromagnetic waves encounter many small obstacles smaller than the signal wavelength, the electromagnetic waves scatter into many small reflective waves and damage the main signal. Refraction occurs when the radio frequency signal passes through the medium of different density than the original medium. Refraction causes the primary wave changes direction. And finally, diffraction, when electromagnetic waves encounter an obstacle with sharp edge that cannot be penetrated, the electromagnetic waves wrap around the obstacle to reach the receiver. In summary, all these signal changes cause multipath interference and attenuation. As you can see, this is the same representation on the previous slide regarding attenuation caused by free space path loss, with additional loss of an obstacle. We are going to use the values to do the math. For example, in the previous slide, we evaluate the loss on the first meter. After that, we demonstrate what is the effect to double the distance. We saw a 6 dB of loss. But now we are going to see that the math is very simple. We are going to evaluate the loss after the obstacle. It is only doing the math with additions and subtractions, which is 61 dB of loss because the 3 dB of loss. There are two ways to improve the radio frequency propagation: active and passive. Active means you can increase the transmit power. Obviously, it will depend on country regulations. Passive, use the proper antenna to focus the radio frequency energy where is needed. It will depend on antenna pattern and antenna gain. dBi is a relative measure to represent gain of the antenna in comparison to an isotropic radiator. dBd is a relative measure to represent gain of the antennas in comparison to a dipole antenna. The most common antennas are dipole antennas. Induction of electricity causes perpendicular magnetic fields. This is the principle of antenna pattern, as you can see here. Basically, the antennas could be grouped into types: omnidirectional, equal signal sent in horizontal directions, therefore less signal is propagated vertically. Directional, directs the signal mainly in one direction. "3D antenna radiation patterns are represented for perpendicular planes. Imagine you have an electric and magnetic field cuts, so you can represent these cuts as a polar chart. as you can see here. Take as reference the 10 dB right and the 0 to say that the gain of this antenna is in average 2.2 dBi. In this case, take a reference the 10 dB right and the 0 again to say that the gain in this pattern is in average 8 dBi. Blue lines represent the intersection points and the angle degrees where the signal is down 3 dB from the main lobe. So far, we have been talking about one of the aspects we mentioned at the beginning, range. Now we are going to learn about the other aspect, data rates, and how they are obtained. To do so, we need to understand the radio frequency waves. First step is understand waveform characteristics. For example, frequency. Just as the name implies, it is something that happens over the time and it could be repetitive. A standard measure is hertz. Frequency and wavelength are inverse related. Higher frequency, less wavelength, and lower frequency, more wavelength. Phase involves the relationship between two or more signals that share the same frequency. The figure represents a change on phase for that wave. Phase is the same frequency, same cycle, same wavelength, but are two or more waveforms not exactly aligned together. What is important to understand is the effect that phase has on amplitude when a radio receives multiple signals. We can use a tool to show some effects of gain and cancel each other when we use phase. This tool is called M&E. So for example, we are going to use these graphics in order to understand the phase. For example, if I have 180 degrees of phase between one and the other one, we can cause something called as a cancellation. Okay. Let's go back. The other characteristic of the radio frequency wave is the amplitude, is the height, the force or the power of the wave. We can obtain the wavelength for the different frequencies. In this case, we are going to use, for example, the 2.4 gigahertz and the 5 gigahertz band. Wavelength has a formula. When wavelength is represented by the lambda, and it is equal to the speed of light divided by the frequency itself. In this case, we can use, for example, the 2.4 gigahertz. If we substitute those values, we have the speed of light is the following. In meters divided per seconds, meters per seconds. And the frequency is which is times per second. Okay, so if we use, for example, the same formula that we have here, so we will have lambda is equal to meters per second divided by times per second, which is at the end represented in meters. So if we substitute all these values, we will have the following information. For 2.4 gigahertz and for 5 gigahertz, which is equivalent to the following: centimeters and 6 centimeters. 12.5 centimeters of 2.4 gigahertz band. This is the value for the wavelength in that frequency, and 6 centimeters for the 5 gigahertz frequency. To transmit the digital information through the air using the radio frequency waves, which are the carriers used to modulate that data. Modulation means to change a carrier signal by varying one or more properties of a periodic waveform. Different modulation techniques represent different ways to shape electromagnetic radio waves. The most common used on wireless communication is called quadrature amplitude modulation, or QAM. The amplitude and phase is changed to indicate binary bits. Quadrature is when two signals are 90 degrees apart in phase. In fact, cosine and sine waves are in quadrature. We can use again the tool called Manning. We are going to use the same wave 2 and wave 1, and we are going to use a phase of 90 degrees of difference, so we can understand what the I and Q components means on the quadrature itself. IQ components are easily represented as something called modulation constellation. So you can see here the modulation constellation representing 2 bits, for example. In this case, this value 1 to 1 means that the component I and the component Q are normal. In this case, the component I is inverted and the component Q is normal. It cuts in different degrees. For example, this cuts in 45 degrees. It cuts in 135 degrees. This one represents the I and Q components inverted, and it cuts on 225 degrees. And the following is the component I normal and the component Q inverted. It cuts at 315 degrees. I and Q signals on their own are not very interesting. The interesting thing happens when I and Q waveforms are added. It results that any form of modulation can be performed simply by varying the amplitude, only the amplitude of I and Q signals, and then adding them together. If you take I and Q signals of equal amplitude and add them, the result is a sine wave with a phase that is exactly between the phase of the I signal and the phase of the Q signal. So you can see the different phases. Comparing the quadrature PSK constellation with the binary PSK constellation, the margin for error is less because there are more possible data points. The margin of error here and here, and the error magnitude here is very different. However, QPSK is also twice as efficient as BPSK because the same carrier signal can represent 2 bits instead of 1. Modulation methods with more data points can represent more bits, but they require better signal quality for the receiver to understand what data was transmitted. There are more complex and robust modulations to achieve better data rates. This example illustrates 2 at 4 bits modulation. It means 16 QAM. So you can see the error vector magnitude is less than the other previous ones. The more bits per symbol you are coding, the better data rates you get. So far, we have covered the explanation about these two aspects we mentioned at the beginning of the presentation, range and data rates. Now we need to understand how they are related. Just like in a real target shooting, as the distance increases, it also makes it harder to exactly shoot every time. We are going to show an example, for example, for BPSK, and explain what happens with the distance. For example, let's assume that this shooting target is BPSK. We have this error vector magnitude. If we go far, we can still have some kind of precision because the error vector magnitude is larger. Okay. But what happens if we use a different modulation? Let's say the error magnitude in the QPSK is different. So the distance, let's see what happens. It's still possible to see the error vector magnitude. It is very possible to shoot in the right position, but let's see what happens when we have, for example, 16 QAM. So we have to divide these. It's gonna be more complicated, right? gonna be more complicated to do so. So, what does it mean? The same thing is true in wireless communication. These dots show a 64 QAM constellation, which is basically 64 targets. 11AC takes this to the next level with 56 QAM, or translated to the shooting target, 256 targets. If I take the same shooting example, I need the precision of a sniper shooter to make no mistake. If I make an error, it means there is something going wrong. In wireless, any noise can confuse the receiver and cause this error and forcing us to lower speed. Because of several features introduced since 11N amendment, modulation and coding scheme was defined, and it is based on several factors to express different data rates. Depending on that, modulation, numbers of spatial strings, channel size, and guard interval. In summary, you will need to have an excellent signal-noise radio to use those highest modulation data rates. Thank you, and I hope you enjoyed this lesson.